Today we're going to be covering Chapter 8C. In this chapter, we're going to be thinking about using different compounding periods than annual compounding periods. So far, everything we've done has been with annual compounding. That means we're getting our % interest per year, and we've measured time in units of years. So now, because we want to get more real-worldy, we want to be more flexible, and we're going to have to address a lot of things that happen in the real world, like quarterly compounding, daily compounding, even continuous compounding, and weird things like this: annual compounding paid semi-annually. So the good news is that everything we have done mathematically so far can be generalized into any compounding period. Shorter, longer, doesn't matter. How are we going to be able to deal with different compounding periods? We're just going to change our time units consistently. So this is going to work exactly like doing calculations in inches instead of feet, centimeters instead of meters, something like that. So that's all we have to do, is be careful about our time units. So two important things that we've got to watch to make sure we've got consistent time units. The first one is really well illustrated with an example. So let's say we have quarterly compounding. What we mean by that is we get our % interest compounded quarterly. So more specifically even, we'd say we get our % every quarter instead of every year. So that's what we mean when we say our % interest compounded quarterly. And when we do this, we say that R is the native interest rate for quarterly compounding. So this terminology is going to be important. So let me highlight that by underlining it. The interest rate that we use with all of our time units being consistent is called the native interest rate. So in this example, it would be our native interest rate for quarterly compounding. Second thing we want to be aware of is now for any compounding example, monthly, quarterly, daily, 2 yearly, doesn't matter. T equals 0 is going to be now. We're going to start all our projects now, starting at T equals 0, which is also always going to correspond to end of period 0, or EOP 0. T equal 1, instead of meaning a year from now, it's going to mean one compounding period from now. So if we're measuring time in quarters, T equal 1 will mean 1 quarter from now. So we want to be careful about that. So let's do this. Let's write this down. If measuring time in quarters, so if we're measuring our time in quarters, for example, T equal 1 just means 1 quarter from now. And while folks are writing this down, let me remind you, your questions are always welcome. Just go to Slido week 7, raise your hands. Either one is fine. All right, let's do a couple of examples illustrating how this native interest rate business works. So if we have a problem where we say we've got 5% equal R compounded annually, time measured in years, that would be exactly what we've done to date, okay? But in the real world, we're going to find cases that look like this, where we say R is equal to 6% compounded monthly. We're measuring time in months. So that means every month you get 6% interest instead of every year. And we could also encounter a real-world problem where we have something like this. The R is equal to 2% compounded quarterly, and we're measuring time in quarters. So you always want to be consistent with R and T, and as long as you're doing that, all the equations we've used so far still work. All right, let's do a quarterly compounding period example to illustrate how all of our math that we've learned so far is still going to work for any compounding period. So let's look at now a 3/4 mortgage. So we're going to go back to Mr. Small Net Worth, and a new lender called Big Shark Lenders has come on the scene and said, hey, we can loan you that same $30,000 as that other stinking mortgage company, but you want to work with us because instead of making payments every year, 3 of them in total, you're going to make us just 3 payments, but you're going to be done in 3 quarters. You're going to make 3 payments, 1 at the end of each quarter, and then you'll own your shack free and clear with no mortgage, etc. So the details of this contract, if Mr. Small Net Worth accepts it, are he's going to pay back, so he's got this $30,000, he's going to in return make them 3 equal quarterly payments with 10% interest compounded quarterly. Sounds like the other deal, but better. The other lender was charging 10%. So this is let me just write this down in our nice mathematical way. So we have R equals 10%. We'd say it like this, compounded quarterly. And we want to know how much would each quarterly payment be. So this is very similar to what we did with Mr. Small Net Worth previously, assuming we were measuring time in years and we had annual compounding. All right, so our fundamental discounting equation simplified for uniform future payments, 74D, still applies. It's still true. We're just using different time units. We're just computing in inches compared to feet, quarters as compared to years. So 74E would also work. I'm going to solve it with 74D. You can verify it with 74E, okay? So we're just going to use our native units. So like we said on the prior page, R equals 10% compounded quarterly. And T equal 1, of course, means 1 quarter from now. And now let's apply 74D. And that's going to give us our CF0, which we know is 30. And I'm just going to expand out this summation notation, putting in everything I know, CF. I don't know CF, that's what I'm solving for, times, what do we got here? We've got 1 over 1, so that'll be the first payment, 1 over 1.1 plus 1 over 1.1 squared. That'll be the second payment, discounting that back by 2 periods, plus 1 over 1.1 cubed, discounting that back by 3 periods for that third payment. And that leads us to CF is equal to through the awesome power of algebra, once again, 30 divided by this big mess. And let's see what we get for that. All right, and we get, shockingly, $12,060. And this is that's the same amount we got with the annual pay lender. So clearly, this is a better deal for Mr. Small Net Worth. He's done with this in 3 quarters. So what's the fatal flaw with that line of reasoning? The initial lender, the legit lender, the first thing the legit lender figured out is about how much Mr. Small Net Worth could pay per year without going bankrupt. So if he can pay about $12,000 a year without going bankrupt, he can't pay $12,000 a quarter without going bankrupt. It's way too much. He will definitely default. And that's actually the business model for these loan sharks. They charge in such a way they know that the counterparty can't execute, and then they come along, they break a couple legs, and in this case, they take title to the shack also. So what do they get? They probably get 1 or 2 payments, and they get the shack. So definitely this would be a bad idea for Mr. Small Net Worth. So let me put that in here. So this would be bad. So that would be a bad deal. But as you see, all the math that we've learned so far, as long as we're dealing with our native interest rates, right, carefully translating R and translating time, everything we've done before still works. And as usual, if you need more time with any slide, just raise your hand. Happy to take more time. Okay, next up, we need to learn about what we call equivalent annual interest rate. And in finance, very often, and you'll find in the real world, even if you are a human resources major, a marketing major, doesn't matter, you're going to have to be comparing financial projects that sometimes have native interest rates measuring time in quarters compared to alternate projects where time is being measured in years or months or something like that. So we need some way to make apples to apples comparisons of these disparate projects with different measurements of time, and the EAIR is the thing that lets us do that. So first of all, what does EAIR stand for? It stands for equivalent annual interest rate. Some textbooks call it EAR. Most of them call it EAIR. Good to know both, maybe. And again, this is the thing that is going to let us make apples to apples comparisons of projects with different measurements of time, different compounding periods. So definition of EAIR, which is really cool if you're a finance nerd. The EAR is kind of magical. It's the interest generated per dollar over a year for a project, irrespective of compounding period. So it's what lets us compare any project with any compounding period, any R. Just exceptionally cool. And not only that, it gets even cooler because the equation for EAIR is pretty simple. The equivalent annual interest rate for any project is equal to 1 plus the native compound interest rate raised to the number of compounding periods per year minus 1. So very simple. This is definitely something to put on your cheat sheet for exam 2 and probably exam 3. This is something we'll be using a lot. How do we describe EAIR in words? X% interest compounded annually, just like the annual problems we've been doing all along, because it has transmorgified our native interest rate into its annual equivalent. All right, let's look at some examples. So first of all, to paraphrase Ronald Reagan, maybe trust, maybe don't trust, but definitely verify. Let's make sure if we put in 1 year in, we get 1 year out. So if we start with a native interest rate of 10% compounded annually, we better get an equivalent annual interest rate of 10%. So let's see if we do. 1 plus 10% raised to the 1 minus 1. And I think you'll see if you do the algebra on, the arithmetic on that, it's pretty straightforward that you do get 10%. Let's do another one. 10% compounded quarterly. What's the equivalent annual interest rate? What interest will we be earning per dollar per year on this? So we're going to have 1 plus 10% raised to the 4 minus 1. And before I put in the answer, let's note here, this is original small net worth mortgage lender. Okay, 10% interest a year, and this is going to be Big Shark. Okay, so let's go ahead, as usual. I would say in my case, I would change Reagan's famous statement to don't trust and definitely verify when you're talking about anything I say. And we get, wow, okay, we get 46% here. So the annual interest rate on the Big Shark version is 46%. And by the way, in consumer product land, that would be illegal. There are laws called usury laws, which do limit the amount of interest that lenders can charge just for consumers. Business to business, you can do anything, but for consumers, and that right now, I think it's somewhere around 35%. So this would be an illegal deal. All right, next up, we need to learn about what we call nominal APR or APR. And what does that stand for? So nominal APR stands for nominal annual percentage rate. And what this is defined to be is our native interest rate times the number of compounding periods per year. So this definition we need to know also. And we need to know one important real-world feature of nominal APR. Whenever you hear nominal APR, everybody agrees that it means your native interest rate times the number of compounding periods per year. However, often you'll see in advertisements and other places folks using the term APR instead of nominal APR. And unfortunately, depending on who's making the advertisement, they mean either nominal APR or EAIR. So that's something in the real world you got to suss out. There's no way around it but to just go ask the advertiser, do you mean EAIR or nominal APR? Our convention, to keep it simple, is whenever we see APR, we mean nominal APR, we mean native interest rate times the number of compounding periods per year. Let's do some usage examples. If we have a native interest rate of 7% compounded annually, what's the APR and how do we describe that in words? Okay, so we just use our equation, which is APR is equal to R times the number of compounding periods per year. So in this case, we have R is 7, number of compounding periods per year is 1, so 7% times 1 is 7%. And so in this case, the APR is equal to the native R. And in APR terms, we describe this as our APR is 7% with annual compounding. All right, let's do another one. So we've got a problem where the native R is 10% compounded quarterly. What's the APR? How do we describe it? So We're going to plug in our equation to get our APR, so 10% times 4, or 40%. And the way we describe this is our APR is 40% with quarterly compounding. And one other thing I'd like to point out here, what I'm showing on the next line is, of course, that we can always so whenever we're given an APR, we can, of course, work backwards to get R. Just say that R is equal to the APR divided by number of compounding, the number of compounding periods per year. All right, so the big news about APR, it's common, but usually not very helpful. So it inherently is not capturing the awesome power of compounding. So it's always going to be an estimation. It's virtually always going to be wrong. And the way that it's going to be wrong is that it almost always underestimates the equivalent annual interest rate. And this benefits lenders. So if lenders just quote the APR, they're not really telling you how much interest you're actually going to be paying. Okay, so that's not good. So what are we going to do to get over this problem? How can we make the APR useful? So what we're going to do is squash it like a bug. We're just never going to use APR. If you use APR in any of our mathematical stuff, any of your functions in Excel or on your financial calculator, you get the wrong answer. So first thing, see an APR, squash it like a bug. Convert it to an R, okay? So we're always going to convert to R, okay? And let's write this down. APR does not work in math. Okay, so if you use APR, you're guaranteed to get the wrong answer, okay? Financial calculator, Excel functions, what we're doing here, the original equations, going back to first principles, et cetera. So squash it like a bug, and here's an example. If we have an APR of 24% with monthly compounding, we're going to get our native R by taking the APR divided by the number of compounding periods per year, and in this case, we'll get 2. So we'd say R equals 2% compounded monthly. And then, if we need it to solve a problem, once we've got our native R, we can do anything. We can, for example, compute our equivalent annual interest rate. So using this above example, the EAIR is going to be 1 plus 2% raised to the 12 minus 1. And if you calculate this out, I've done this once this morning, so I don't need to do it again. 26.82% is what I got when I wrote the notes and again this morning. So that's what we'll do with APRs. So another quick interesting note on APRs, Elizabeth Warren, for better or for worse, before she got heavy into politics, she was a big advocate of trying to do away effectively with APR and say that any lending companies could quote their APR, but they also had to state their equivalent annual interest rate. That turned out not to get passed, but it's an interesting thing that she tried and failed at that. Okay, so there is a great question here. What if we've got a problem involving both annual and quarterly, okay? And here's the answer to your question. You ask, I'm here to help, okay? So we've got a problem here which says which money market offer is best. So you are thinking about putting your money into a market, money market fund. So let's rewrite this as what is best place for you to put some cash. So you got two banks. This is very much a real world kind of a problem. One is offering you 5% compounded annually, and another bank says in their ad, we're offering 4.5% APR with monthly compounding. All right, so let's see which one is best. Okay, so the EAIR for Bank 1, you want to notice here, Everything is stated in annual terms, so clearly they're measuring time in years. They've already got a native R measuring time annually, so in this case, the APR is equal to R, which is equal to 5% compounded. So the APR is equal to the R, which is equal to the EAIR, 5% compounded annually. All right, so that makes it easy for bank one. So for bank two, now we have to sort this out here. So the APR is equal to 4.5%, and let me just put in here with monthly. Okay, so R is going to be equal to APR divided by the number of compounding periods per year. So that's equal to 4.5% divided by 12. And I'm not sure what that's equal to right off the top of my head, so let's go ahead and compute it. Okay, so it's 0.375% compounded monthly. So bank two, what they're really offering you is every month you're going to get 0.375% interest. And that's nothing wrong with that, that's fine. But we want to compare it to bank one, right? So what do we got to do? Get the equivalent annual, see how much interest you'd earn over a year, yeah.
So every R up until now is annual compounding?
Has been annual, everything through 8B has been, yeah, good question.
And every question from now on out, we're trying to get to that?
Yeah, so you'll have to see, like here, for example, so if you just get something like bank one, you pretty much know there is nothing mentioned but annual. The native R is already measuring time in annual terms. However, if you didn't get that, what you'll find with this, if you do the math, is the APR is also 5%. 5% divided by one compounding period per year is 5% rather. You'll also get, if you plug in the EAIR formula, 5%. So the math will help you. You sort of can't screw it up, right, no matter what. So you may see going forward stuff like this, or you may see stuff like this, and you'll know it's an APR and you have to convert it to an R. Why? Because I'm always going to say APR. You know, you have to say APR, and I'm not going to try and trick you guys. Yeah. Does that make sense? Yeah, okay. And then the only way you can get an equivalent annual interest rate is from a native R, not from an APR. So find the APR, squash it like a bug, convert it to an R, and then if you need to, get the EAIR. Yeah, good question. All right. All right, so now we've got our native R, and we can compute our equivalent annual interest rate, which is 1 plus our native R to the number of periods per year minus 1. And in this case, that's equal to 1 plus 0.375% raised to the 12 minus 1. And I have no idea. My early onset Alzheimer's is kicking in, so I don't remember from section A, so let's just see what we get. 4.59%. Okay, so if you put your money into bank one, it's going to be growing at 5%, bank two, 4.6%. That sounds pretty cool. So how many prefer bank two? How many prefer bank one? Absolutely. Okay. So I'm here to tell you that in Section A, there were two people. I wrote down their names, but I won't repeat them for you, who actually said bank two. So I think it was early. They didn't have coffee, whatever. I won't hold it against them. But I did say that I would like to talk to them about some financial products I'm offering to give them after class. Okay. So clearly, bank one offers a better deal. And why is that? Because it's building you the bigger pile of money after a year, right? So this is a very real world type of problem. This sort of thing happens in the real world all the time. Okay, so I've got a few rules here for using APR-R and EAIR. So first is, as we have been saying, APRs are inaccurate. They'll give you wrong answers. So always convert them to native Rs, right? And just use that very simple, R is equal to APR divided by the number of compounding periods per year. And then whenever possible, you're done. Just plug in the math, find out what you got to find out, use the same equations that we've learned and know and hopefully love from chapters 8A and chapter 8B. But sometimes you need to find the EAIR, and in that case, go ahead and compute the EAIR. And for you finance majors out there, I explain why I've developed these rules. You can get some wrong answers if you don't follow these rules, so just follow these rules. All right. So next up today is probably the most important application of APR and EAIR, and this is what we call semi-annual bonds. So semi-annual bonds, as you might suspect, pay interest twice a year, and most corporate and treasury bonds are of this type. So this is going to be a very important class of problem for us because you see it everywhere. Most, I want to say even almost all bonds are of this type that you're going to see at Interactive Brokers, JP Morgan Chase, et cetera, et cetera. So we need to know how they work. Okay. All right, so let's see what we're talking about here by looking at a cash flow diagram for an 18-month semi-annual bond. So this is describing what's written in the contract, okay? So we're going to start here with the bond purchased at issuance. So this is case A. We'll look at case B in a minute. So we want to look at, in this case, the full contract. So this will be for someone who buys the bond when it's issued and holds it through the whole contract. Okay. All right, let's see what we got here. So at t equals 0, they buy a bond. Okay, so this is called the principal or face value. So this is the issue price of each bond. The contract says that Tesla is issuing 1 million 18-month bonds, semi-annual pay bonds, with a price per bond of $1,000. Or they would say with principal amount per bond of $1,000, or face value per bond of $1,000. And then if it's a semi-annual pay bond, every 6 months in this contract, you're going to get an interest payment. So if you keep holding this bond, you get an interest payment in 6 months. You get another interest payment 6 months later. And then after that, the contract ends. And you get the final interest payment. So at the end of the contract, you do get a final interest payment. And then you get your principal or face value. Which is, again, the issue price of the bond. So this is all stipulated in the contract for each bond when it's issued. Okay, excuse me. So our second case that we're going to have to consider is a bond purchased in the marketplace. And this is at, let's say, for example, 6 months and 1 day after issuance, and let's say same bond. So let's look at the same bond, for example, purchased in the marketplace at 6 months and 1 day after it's been issued. So what we've got here is the price paid for the bond by whoever is buying it now. Let's say we're all buying it collectively. We each put in a little money and we're getting this bond. And it's probably not going to be the face value, right? So remember we saw with the HCP example, the face value of those bonds, the principal was $100 a bond, and in the marketplace, the price had changed, and I think we paid $92 a bond, something like that. All right, let me also put in here what's happened previously. So in the red here, I'm putting in history. So this is going to be the first 6 months, and here's going to be whoever bought it at t equals 0, the principal or face value that they paid, and then yesterday they got an interest payment, and they sold the bond to us. So they got that CF0. So let's put this in. So this is t equals 0, okay? This is all history, which we don't care too much about. I just want to show you what's been going on with this contract here, okay? And here we have, so when it's issued, whoever's buying it is paying that principal, right? And then they got, yesterday, they got that interest payment, and they also got CF0, which is not equal to principal. CF0 is what they sold the bond for. That's what we paid for it in the marketplace today. And, you know, it might have been 1,000, but that would just be a coincidence. So now we own this bond. We just bought it today. Interest was paid yesterday, so guess what? In 6 months, we're going to get the contractual interest payment, right? And then in another 6 months, we get our final interest payment and the principal, because those are the things in the contract. These are transferable contracts, so we get the interest payment specified in the contract, and at the end, we get a final interest payment and the face value. Okay, before we can go any further into these ubiquitous semi-annual pay bonds, we need to know some basic vocabulary. So the folks in what I call bondland who specialize in this type of bond have developed some vocabulary around these semi-annual pay bonds, and we need to know it. So heads up, on exam 2, you will need to know this vocabulary. You can have a helper sheet again, so I would recommend that you go ahead and maybe put this on your helper sheet or memorize it. Question? Oh, yeah, absolutely. But I don't do sign language, so, but I'm always happy to go back. If you can vocalize it, I can do it, yeah. Always happy to go back, just ask. Got it. Okay, great. Let's move on. All right, so let's do this vocabulary. So principal or face value, as we've seen, it's the amount that the issuer borrows per bond, right? And it's also the amount that's going to be repaid at the end of the contract, and that's going to be along with final interest payment. Okay, they also have a thing they call the coupon. The coupon of a semi-annual pay bond is the total dollar amount of interest paid per year, which is a weird thing because they pay half of that every 6 months, okay? So the coupon is the total amount paid per year, but it's actually paid in 2 tranches every 6 months. The coupon rate, what they call the coupon rate, is what we would call the APR of the bond. The coupon rate is the bond APR. So the way they describe that is X% interest with semi-annual compounding, and we can compute this as just the coupon divided by the principal. Okay, and then finally, we can compute what they call yield to maturity for a semi-annual pay bond. To us, that's just the equivalent annual interest rate. They call it yield to maturity, it's equivalent annual interest rate. They mean the same thing. Okay, before we solve some problems, let me go back to the questions for a second. Why was the last problem bad for Mr. Small Net Worth? So the original lender for Mr. Small Net Worth estimated that the most he could pay per year without going bankrupt was around $12,000. So Big Shark was offering him a deal where he would have to cough up $12,000 every 3 months instead of once a year. That's much more than he can afford. It pretty much guarantees he would default on the contract. So if they decided not to break his legs, they would get the title to the shack, right? Probably they'd get one payment beforehand. And that's kind of the business model of Loan Shark. Make a loan that people can't pay back, get a couple payments, and then get the car, get the house, get the whatever it is. All right. So doing our at issuance problems, we're going to do problems in both cases, at issuance and trading in the marketplace. So remember, the bondholder is paying the principal to get each contract, and at the end of the contract, the principal will be repaid. So depending on what you find when you're looking at these bonds at Bloomberg or Interactive Brokers or Schwab or whatever, they're never going to tell you everything. So you may have to calculate the coupon. That's the coupon rate times the face value. You may be asked to or need to compute the coupon rate, which we know as the bond APR, and that's just the coupon over the face value. And then the native R, we can get, in this case, from the coupon rate divided by 2 periods per year. And this is only going to work for at issuance problems. Okay, so this is really important to remember. And then, once we know the native R, we can compute the yield to maturity. All right, with all that in our pocket, let's do an example for a semi-annual pay bond where we're going to buy it at issuance and hold it through the whole contract. So SimpleCo is issuing a 7-year bond with a $1,000 face value per bond and a $100 coupon. And this is a semi-annual bond, so clearly the coupon is going to be paid in 2 blocks every year of $50 each. Okay, so let's find the coupon rate of this bond, the native R, and then the yield to maturity. All right, let's see what we can do here. So we have 100 coupon face value of 1,000, and we've got 50. Okay, so the coupon rate is just equal to the coupon divided by the face value. And so that's equal to 100 over 1,000, and that's just 10%. Looking good, okay? And now let's find our native R. So we just got our APR. The coupon rate is the APR. So for a bond at issuance, only, we can take that coupon rate and divide it by 2 periods per year. So we get our 10% divided by 2, which is 5% in most circles. And now we have enough to plug in our EAIR formula to get what the bond people call yield to maturity. Okay, so let's go ahead and do that. So we have 1 plus 5% raised to the 2 minus 1. And I better double check that one. All right, 10.25%. Awesome. So that's how fast your money is going to be growing actually in this contract if you hold it for the whole time. And the coupon rate, the APR, is less than that. So as usual, the APR is wrong, and the APR is underestimating the actual amount of annual compound interest. All right, let's see if we can solve an after issuance bond problem. So in this case, remember that the price of the bond is going to be determined in the marketplace, and it's not necessarily going to be equal to the face value. So we have a situation like this. So we have CF0 here, which is not, it's going to be the marketplace price here. And again, it's not necessarily going to be face value. It's whatever we agree in the marketplace to exchange the contract for. And then all of the initial contract terms for the issuer are still in play. It doesn't matter who owns the bond. It doesn't matter what they paid for it. The contract says they pay this amount of interest every 6 months, and the face value is, say, 1,000. At the end, they also, along with the final interest payment, pay the 1,000 back. So the implications of this are we cannot compute the native R by just saying it's the coupon rate over 2. We're going to have to compute it the exact same way that we did this in 8b. We're going to have to write an algebraic equation and plug in for R until we get the right number. You could use goal-seek in Excel. On an exam, it'll be a multiple choice. We'll do an example seeing how it works. Okay, so in this case, you will need to calculate some of the contractual information will be missing. True at Interactive Brokers, true anywhere you look, so you got to compute some yourself. So for the coupon rate, and the semi-annual payment, those are all the same because those are contractually specified. So the way we compute those is the way we've always computed those. You're definitely going to have to compute the semi-annual native R. No ifs, ands, or buts about it. And in this case, you're going to have to write an algebraic equation for that and plug in and see what the right answer is. And then also, ultimately, our goal is the yield to maturity. We want to know if we buy this bond at this price, at what rate annually compound is our money going to grow? And that's the YTM or the EAIR. All right, so let's see if we can do an example of this. So here's what we're given. All right, so long ago and far away, January 1 of 20X1, SimpleCo issued a bond maturing on January 1 of 2007 with $1,000 face. So everybody who bought a bond paid $1,000 and a 10% coupon rate. And today is January 2, 2000X6. And the bond is trading, so we could buy it for $950 here. So let's just put in a few things we know here. So interest was paid yesterday. Okay, so if we're at the second day of the month, the interest was paid yesterday. So now let's see if we can find a cash flow diagram for us, if we buy it today, the semi-annual interest payment, an equation that can be solved for R, and then let's show that if we have the right equation, it illustrates that the actual compound native interest rate with semi-annual compounding is 7.796%, and then let's use that to compute the yield to maturity. All right, so let's start with the cash flow diagram. So I need to know how much longer this contract goes before I can do this. So let's see if we can figure it out. So today is 2x6, so interest was paid yesterday. So the next interest payment is going to be at July 1, right, 6 months out, July 1 of 20x6. Then I go 6 months after that, and I get to January 1 of x7, and that's when the contract ends. So I know I've got to go out 2 more payment periods. So let's see how that looks in a cash flow diagram here. So I'll do it over here. Get my little arrow tool going here. So I got that, and so I'm going to pay this for it today, and then in 6 months I'm going to get an interest payment, and then at the very end I'm going to get an interest payment and the face value. So let's put in here, so CF0, so this is what we'd be paying today for this, and this date is 1/2x6, and this date is 6 months later, and then the contract ends on 1/1x7, okay? And we'll fill in, we want to know all these numbers, so we do know, we're already told that the principal is 1,000, so that'll be coming back. We got to figure out what these interest payments are, but we'll get there. So for B, we're asked to find the coupon. So we know the coupon rate, I think. Let's see what we're told here. Yeah, 10% coupon rate, 1,000 face value. So the coupon is equal to the coupon rate times the face value, and that's equal to 10% times 1,000, and that's equal to 100. So remember, that is paid, half of it is paid every 6 months. So the semi-annual interest payment is the coupon over 2, that's 100 over 2, and that's equal to 50. So now I can go up here and say int equals 50, and let's put another 50 here. So now we're able to complete that cash flow diagram. It's got everything we need. It's got the time, it's got the cash flows, and we also know here that CF0, I think what the marketplace price is $9.50, yep. So let's put that in. So now we know everything we need to know. All right, so now we want to compute the native interest rate. And we're going to use our fundamental discounting equation. So we know that CF0 is 950. And we know that in one compounding period, we're going to get 50. So we need to discount that back by 1 plus R. I'm going to call that RR, raised to the 1 for one compounding period. And then plus, we're going to have 50 plus 1,000. We get that principal back and the final interest payment, divided by 1 plus RR raised to the 2, because that's coming into the second 6-month period, right? Okay, and now what I'd like to do with this one let's substitute in, and I'm going to put a question mark here. So for RR, let's put in 7.796%, and let's do it again here. And let's see if that's true. Let's see what we get. I'm going to throw it in the calculator. right, I get 950. So all right, so we got Yahoo, we got our native R in semi-annual compounding, and now we can get our YTM. Yield to maturity is just the same as EAIR, so that's 1 plus R to the 2, in this case, minus 1, and that gives us 1 plus 7.796% raised to the 2 minus 1. And I'm going to plug that in again, because as they say when it comes to me, don't trust and definitely verify, blammo. And I get 16.2%. Okay, so that's how we're going to deal with these semi-annual pay bonds at issuance and also trading in the marketplace. Count on problems like this on exam 2, one for at issuance and one for trading in the marketplace. So that hopefully will be helpful to you. So before we go, I have a couple more things to do. This is, of course, as far as we got in section 1. As usual, they're not quite as hip as you guys. They need more coffee, but don't go yet, because I do have one more interesting thing to show you. Plus, I want to answer some questions. Does the raise to the 2 periods per year always just equal 2? No, no, no. For semi-annual bonds, it equals 2, because that exponent is always the number of periods per year. So if we have an APR that's talking about compounded, not compounded quarterly, with quarterly compounding, how many periods is that per year? 4. Monthly compounding, 12. So the exponent would be 4 or 12 in that case. Good question.